Okay, welcome back. In this lecture, we're going to be talking a little bit more about AVL trees. You've already seen the basic ideas about how to deal with the algorithm itself. We're kind of going to delve a little bit here into a bit of theory, not a whole lot of math, but just pretty much kind of talking about AVL trees from a different point of view and looking a bit at why the algorithms work the way they do and what patterns you can expect to see as you do an insert and a remove. So we'll start by talking about insert. And the way I'm going to start talking about this is to draw 4 trees. This tree, this tree, this tree, and this tree. And you can look at each of these and notice that, okay, here we've got height 0 and a balance 0, and of course this is the same tree. Here we have a height 1 on this node with a balance of -1, and a height 1 on this node with a balance of +1. So we're concerned here about the root of each of these subtrees, and of course, here the root is the only leaf, or the only node, and then here that's the root, and it's got 1 leaf. And so as we start to insert into these trees, one thing you can take note of here is, well, when I insert here, anytime you insert, you're always going to insert as a leaf, remember, that's how binary search trees work. You will always have a balance of 0 and a height of 0 on every leaf. And since you're inserting on a leaf, the node you insert will have those properties. And you can say here then that that's going to change this height to 1, and will change this balance to -1. And likewise, if you were to make the same insertion as a right child of this node, you'd have here the balance becomes +1, and the height becomes 1. And you can do similar things down here, except in this case, only the balance would change and not the height. I can insert as a right child here, in this case. That changes the balance from -1 to 0. Remember, the balance is the height of the right subtree minus the height of the left subtree. And in this case now, they're equal, so our balance goes from -1 to 0. And in this case, we insert in the left, and likewise, the balance goes from -1 to 0. In both of these cases here, the height of that node is 0, and its balance, whoops, let me do it this way. Height of each node is 0, and its balance is 0, each of the inserted nodes. So what we notice here is that when there were no nodes to start with, then of course inserting the node increased the height. And when we had 1 node to start with, then inserting kept the height the same. And the reason this is relevant to us is because, remember, each of these nodes, unless it's the actual root of the whole tree, is connected by some pointer to some parent node. And the question becomes, does the parent somehow get affected? And it wouldn't if the height doesn't change. If I have a subtree like this, where I say the balance, you have some height 1 here, and some height 2 of this tree, if from the parent's point of view, this height doesn't change and this height doesn't change, then its balance has to stay the same as well. I mean, if you're a parent node and your 2 subtree, as long as your 2 subtree heights remain the same, then your own balance remains the same. And so what this means for us is, of course, that you can't have an illegal AVL tree unless the balance changes, because if it starts as a legal AVL tree and the balance of a node doesn't change, then that balance, of course, continues to be legal. If it was legal to start with, it can only become illegal if it changes. And so as we insert or remove from a binary search tree, we're only going to be messing with 1 subtree. Wherever we stood at this parent node, let's say we went to the right because whatever we were removing or inserting was greater than that parent, well, then we didn't touch the left subtree at all. So we know the left subtree height stays the same because we didn't touch it. We've only been messing with the right subtree because that's where we went for the insert or removal. And if the right subtree height doesn't change, and like, for example, if this was our right subtree, the height there doesn't change, well, then its parent isn't affected at all because its parent knows the 1 subtree didn't change in height because we never even messed with that subtree. And then if this was the subtree we went into to insert or remove from, but its height didn't change, then the parent's balance and height couldn't have changed because its subtrees from its own perspective didn't change. That is, these rotations we've been doing are purely local operations. And from the parent's point of view, if I dump a node into a subtree and that subtree stays the same height as it was before, then as the parent of that subtree, I don't care what happened. The parent would only care if the subtree height changed, because now we say, well, my one subtree stayed the same in height, but this other subtree has changed in height, which means my balance has changed. And now it might potentially be illegal. We need to go ahead and check on those kinds of things. So we're concerned often about whether the height of a subtree changes or not. And we can see in these two cases up here, the height changes, and in these two cases down here, it doesn't. And we can discuss this idea more generally as well, where we can say, let's deal here with the idea of a node that has two subtrees, both of height h, which means this node has height h plus 1, and its balance is 0. So we've got that set up like that. Now, in dealing with this, the situation we run into is, let's say I've made an insertion into, say, the right subtree. And let's say it was an insertion that increased the height of the subtree to h plus 1. Well, if I increase the height of the subtree to h plus 1, notice now, because the height of this parent node is the maximum of these two plus 1, now this height has to be h plus 2. That is, what has happened here is this subtree has increased, which means now the path from this node down to here is larger than, before we had just some sort of leaves on the bottom of these subtrees. But now the newest leaf in the overall tree is one level deeper, which means the height of the root, which is defined as the path to the deepest leaf, of the length of the path to the deepest leaf, that root height now must increase because the deepest leaf is deeper than the other leaves used to be. And that's why this subtree had gone up in height, and now that's why when you take the maximum of the two and add 1, it's going to be 1 more than it used to be. And the balance, of course, is affected as well, plus 1. And note that that's not too different than the situation we had before. If I can throw this picture back up here, where we said the root node starts out having a balance of 0. Its two subtrees are equal in height. In this case, they were both h. In this case, they started out both being -1. When the subtrees are equal in height, and then suddenly they're not equal in height anymore because of your operation, well, there's a few things that might cause that, but if we're doing an insert, there's only one thing that could cause it. And the other thing would be if we were doing a remove. If the subtrees are equal, and then suddenly they're not, either one of the subtrees has grown or one of the subtrees has shrunk. That should hopefully just be common sense. If they're equal and if they used to be equal, now they're not, then one of them has changed. And if we're doing an insert, the only way one of them could have changed would be to have grown in height. You can't do an insert operation and then have, as a result of that binary search tree insert, have a subtree be smaller. That doesn't make any sense. The AVL rotations might later on correct a particular piece of a tree, but we're not talking about that yet. We're just talking about after you've done the insertion itself, what is the result? And if we've done an insertion and one of the tree heights has changed, it must have gotten bigger. There's no way it could have gotten smaller. So in both this situation and this one here, what has happened is the node had two equal subtrees, and then one of them grew. And so if the two subtree heights were equal, and then the height of one of those subtrees grew by 1, then that subtree that grew must now be defining the new maximum height. If you take two elements that are equal and then you increase one of them by 1, well, then that one you just increased is now not only the maximum, but is greater than the maximum used to be. Take two numbers that are equal, 2 and 2, and you add 1 to one of the numbers to get 3 and 2. Well, 3 is not only the maximum now of the two of them, but it's 1 greater than the maximum used to be. And so if the maximum of the two subtree heights is 1 greater than it used to be, then the height of the parent is going to be 1 greater than it used to be. So what this situation defines is a case where we're saying when your subtree heights are equal and you do an insertion that increases the height of one of the subtrees, then the parent likewise is going to increase in height. That's going to be sort of a general rule for us. On the other hand, if we had done had this situation where we had a height h subtree and had a height h plus 1 subtree, then here the balance is plus 1, our height is h plus 2. In other words, we have two subtrees that differ in height by 1. If then I insert into here to make this h plus 1, then that balance goes to 0, but the height stays the same. And that is the same situation we had before that case, which now I'm going to have trouble showing, I guess. Fold the bottom here. But the idea here was that that was that situation as we had before, where in both of the cases at the top of the slide you're seeing now, in both of those cases, I had a height of 1. When I did my new insertion, the height didn't change. And the reason is I was inserting into the smaller of two subtrees. They were not equal in this case. One started out being larger than the other one. And so if you take two unequal subtrees and then you do some operation that results in the balance being 0, as it is here and as it is here, the balance goes from plus or minus 1 to 0. That means you had two unequal subtrees, and now they're equal. And if you're doing an insert, the only way for that to have happened would be that the smaller one grew in height. And then there'll be likewise a similar situation with remove, where the larger one shrank in height. But if you're doing an insert, the only way to go from a situation where the heights are not equal to a situation where they are would be if you inserted into the smaller subtree and made it equal to the larger one. And now the two are equal in height. And if that is what happened, then as you can see in both of these cases and this one down here, the larger subtree was already establishing the height. And so since the larger subtree was already establishing the height, the smaller subtree increasing to be equal to the larger one isn't going to change the height of your parent. All it's going to mean is now when you take the maximum of the two subtrees, they're going to be equal. And so before, there was definitely a maximum. One was smaller than the other. Now they're both equal to the maximum instead of just one. But the maximum itself hasn't changed because the larger subtree already had that value. The small one is just growing to be equal to the larger one, but the larger subtree was already establishing the maximum and therefore already establishing the height of that root. And we've just grown the other half of the tree, this half, or this half, or this half, to now be equal to the first half. What this means for us is that in the top case, the one we talked about before, we can say when the balance of our node, when we're doing an insertion, and the balance of our parent node goes from 0 to plus or minus 1, we also know the height of that parent node must have increased. It happened in all three of these cases. The balance changed, and the balance changed from 0 to plus or minus 1. And what that meant was we went from an equal subtree situation to a situation where one of the subtrees became larger, and because the subtree became larger, the height of the parent changed as well. So we have a sort of a chain reaction here, where the balance changing from 0 to plus or minus 1 means that node has also gained a level in height. Where the other situation, the bottom of that first slide and then this bottom example here, is one where the balance has gone from plus or minus 1 to 0 rather than from 0 to plus or minus 1. And in this case, where the balance goes from being slightly uneven to being perfect, is a situation where you had two unequal subtrees and you inserted into the smaller one to make it equal to the larger, and that means the height couldn't have changed at that parent because the larger subtree already established it. We haven't increased the maximum height of these two subtrees. We've just made it so that when you compare the two numbers, now they're both equal to the maximum instead of one establishing the maximum and the other being one smaller. So the rule is when we're doing an insertion, if the balance of a parent goes from 0 to plus or minus 1, then we would know the height of that parent also changed. And if the balance of a parent went from plus or minus 1 to 0, we know the height didn't change. And actually, not just for parent, for any node. If the balance has changed to minus 1 or plus 1, we know the height's changed. If the balance has changed from plus or minus 1 to 0, we know the height of that node has not changed. And so the last thing we can look at, then, with regards to this, is the only other possible situation. We have here a smaller subtree and a larger subtree. Therefore, that's h plus 2, balance of plus 1. And then my insertion does not happen in the smaller subtree, it happens in the larger one. That makes that height h plus 2. That makes this height h plus 3 with a balance of plus 2. That is now an illegal situation that needs to be repaired, and we do whatever rotation we end up doing. And what this will end up doing, as we saw with rotations, is that'll make the balance 0 and drop this a level in height to h plus 2. That was a general rule for all the rotations we would deal with, except for that one special case we mentioned that we're going to see at the end of today. What we're saying here is that the height is going to drop a level. When you have an illegal situation like this, your rotation will drop your balance from plus or minus 2 to 0, and it'll drop the height one level. And then what would happen would be both of these trees would be height h plus 1. The nodes, some of these nodes here would move over to this side, and that would be how we have this balanced out. But this is just sort of the top level view, not really concerned with what nodes are in the subtrees, but just saying, here's what will happen, is that the balance of the top node here will become 0, and its height will become 1 less than it was before the rotation. It was h plus 3, it comes back down to h plus 2. And you'll notice that's the same situation we had at the very bottom of that sheet when I went over these two examples. Down here, the height went to 0, or I'm sorry, the balance went to 0. The height remained at h plus 2. That is, what has happened here with this rotation is the whole tree started out at height h plus 2. The insertion operation, since it triggered a rotation, any insertion that would result in a rotation has happened because the insertion made one of the subtrees larger, and now the height of that node increased by 1. And now the rotation brings it back down. At the end, the height is exactly what it was when it started, which means the parent of this node isn't going to notice a thing. It's going to say, I had a subtree, and the height is h plus 2, and then I saw the height was h plus 3 for the briefest moment as there was a rearrangement of something, and now it's h plus 2 again. So it's back where it started before the rotation, so that means my balance is okay. Because my one subtree wasn't touched at all, and my other subtree, the one I actually inserted into, it started out being h plus 2, and it's still h plus 2. And yeah, it was rearranging itself for a while, but I don't care. This parent of this node up here, or the parent that we don't really see, but where this pointer comes from, says my subtree started out being h plus 2, and it's h plus 2 when we're done. So everything must be cool. And so that parent's balance wouldn't change. That is, with insertions, we are guaranteed, after you do one rotation, whether a single or a double, and that's why it's very important you understand doubles count as a rotation. You don't count them as two. So when I say insertions will only require one rotation, I mean one of the four we talked about. A double rotation counts as one rotation for the purpose of that statement, as I tried to make clear last time. An insertion operation is only going to require one rotation. And the reason is, a situation that would trigger a rotation would be one where you had this kind of a deal, where there is a smaller and a larger subtree, and you insert it into the larger one, and therefore some node higher up changed from plus or minus 1 balance to plus or minus 2. And that's what happened in the single rotation operation a few lectures back when we first looked at the single rotation. The left subtree of the root had K1 and A and B, and that subtree was one level larger in height than the right subtree of the root, which just was subtree C. And if you go back in your notes, you'll see that on one side of the tree, the right side of the tree, you had subtree C. On the left side of the tree, you had K1 and A and B, and that left side was one larger, and we inserted it into it, and that increased this node. And that's what's happening here, too. And so the idea is when we increase the node height, when we increase this subtree height, the larger of the two subtrees, now the balance goes from plus or minus 1 to plus or minus 2, and that would have increased the tree, the root node of this subtree, and the insertion brings it back, or the rotation brings it back to normal, to what it was before. Because a rotation will drop your tree one level in height, and because the insertion that you would have done before the rotation would have increased that node to begin with, the height of that node, the two cancel each other out. Your binary search tree insertion, if it's one that results in you having to do a rotation. Some of them, of course, won't, so that's a moot point for this particular example. Any insertion that will require you to do a rotation to fix something, that same insertion would have increased that unbalanced node height by 1. And the rotation then will subsequently drop it down 1, so it always will end up being what it used to be. It was h plus 2, the insertion brought it up to h plus 3, the rotation will bring it back down to h plus 2. And therefore, when you're doing an insertion, when that rotation you do is done, that subtree's back to the height it used to be before the rotation, before the insertion ever began. And so from the point of the parent, nothing has changed. And therefore, you're guaranteed you'll only need to do one of those 4 rotations, but only once for an insert. After you do a rotation for the first time, it's going to be, the tree itself will be back down to the original height it was before you did the insertion, and therefore the parent would not see any difference. And therefore its parent would not see any difference, and so on and so forth all the way up. So locally you repair this tree, but there won't be any need to repair anything any higher. That'll always be the case for an insert. Or in other words, what we can do is quickly write out sort of a summary of these rules. For an insert, you will insert as a leaf, that's always the case, and then you will check the balance of new leaf's parent, as we were doing on that very first slide. When you insert as a leaf, you're inserting as one, you're inserting one node with balance and height both 0. But the parent is bound to be affected. And this slide covered all 4 of those cases. In all 4 of these cases, your parent's balance is such that when you do your insertion, the balance is going to be affected because you do your insertion at a null pointer. And so since you're inserting at a null pointer, you're taking this tree that was formerly a -1 in height, and you're making it 0 in height. As a result, since your subtree on this side or here, your subtree has gone from being from height -1, which is the height of a null pointer, to height 0, which is the height of a one-node tree. By definition, that has to mess with the balance of that parent. It has to, because your subtree has gone from null to one node, from height -1 to height 0. And so since the height of one of your subtrees has changed, your balance is going to change. So in all 4 of these cases, the balance changes for sure. What doesn't necessarily change is the height. And so the idea here then is we check the balance of the new leaf's parent, and now we say if balance goes from ±1 to 0, then you can say height stays the same, and you can stop the operation. If it goes from 0 to ±1, the height increases, and you have to continue upwards. If the height increases, that means your parent's balance is affected, so you'll basically go back and now check the balance of your parent. And if you go from ±1 to ±2, then you would do a rotation that brings you down to 0, and so as a result, as we've just discussed, the height stays the same. It doesn't really stay the same, but it increases because of your insertion, and then decreases because of the rotation, so it ends up the same, and then you can stop. So in both cases, if you go from ±1 to 0, whether there's a rotation in between or not, you're going to eventually stop. And if you go from 0 to ±1, it's because you had 2 equal height subtrees, and then one of them got larger, and that means the height of that node did increase as well as having a balance change, which means since you being a tree, since your height increased, your parent now has a subtree whose height has changed. And so you need to go up and check the balance of that parent. And so when you do an insertion into an AVL tree, at that point where you've done the insertion and you go back and check the parents, you'll basically continue on your merry way upwards, checking the balance of the parent, and then checking the balance of its parent, and then checking the balance of its parent, and then checking the new balance of its parent, and so on and so forth, all the way up the tree. As long as you keep hitting a case where your parent's balance or where your balance goes from 0 to plus or minus 1, then you say, okay, check the parent. And it has a balance that goes from 0 to plus or minus 1, so you go up and check that parent, and so on and so forth. As soon as you hit a case where the balance was plus or minus 1 before the insertion, then you know you'll be stopping here, because either it now changes as a result of the stuff below it directly to 0, in which case then the height stays the same and you stop, or that balance changes to plus minus 2, you do a rotation to bring it to 0, and again, then the height ends up being the same as it was before the insertion, and you stop. And we saw that in all these situations. Even going back to this slide, that's exactly what happened here. Whatever we did here, that changed the height from 0 to plus or minus 1, or changed the balance from 0 to plus or minus 1. So the height of this node changed by increasing. Therefore, we'd have to check the parent of this node. Where down here, the height balance went from plus or minus 1 to 0. The height didn't change. We could stop here. The parent of this node would not be affected. The parent of this node would be affected because the height of its subtree, namely this node, has changed, and so this parent has an affected balance as well. And that's always what we're concerned with, kind of conceptually, is whether we have to bother going up and checking the parent. And with inserts, these were the rules that we would follow. That sort of explains the pattern you'll run into when you start to deal with inserts. Removes will be a slightly different pattern. And the best thing for you to do then is, as you use the first two AVL lectures and try and kind of go through some of the examples and see the different algorithm and how it works, then what you can do is you can take note of the fact that this will be the pattern you're seeing all the time. With removes, go ahead and draw. If we have a height of 1 and a balance of 0, because I've got these two nodes here. As opposed to this situation, where I have a height of 1 and a balance of here minus 1, plus 1. So there are 4 possibilities for remove, and what we're going to do is remove a node. If I get rid of this node, my height stays at 1, my balance here changes to minus 1. And likewise, if I were to have gotten rid of that node instead, because these are identical trees at the top, the balance would have changed to plus 1, but the height still stays the same. We're down here, if I get rid of this node, the balance changes to 0, and the height, notice, changes to 0 as well. Now I have no subtrees anymore, so I'm down to basically this being a leaf, and so its height is 0. And likewise, if I were to remove that, this height changes to 0, and the balance changes to 0. This becomes a leaf, so it's got a height and a balance of 0. So what we notice here is it's sort of the opposite of insert. In the case of remove, when I kill this node, when I delete this one, the other node is still establishing the height. So it's safe to remove this node because the other, or I'm sorry, not, it would be safe regardless, but in terms of does the height get affected, I can remove this node without affecting the height of its parent because the parent has this other node to keep the height established. Where in this case, this node was the only one establishing the height of its parent. So when I get rid of this one, the parent sort of loses this extra one edge of support, and the height drops to 0. And this effect can be seen in sort of more general format if we then, as we did with insert, look at sort of subtree examples instead of just very specific down at the node level. If I have this situation where I say here's a subtree of height h, and here's a subtree of height h minus 1, but with a node extra. Here's h plus 1. The balance here is 0. Now, if I were to delete, hold on, let me do this. That means this entire thing is of height h. So the two subtrees are equal, and therefore the balance is 0. Now, if this is the last node keeping that subtree at height h, and I delete that, and now we're just left with this part of the subtree, well, then that is h minus 1, which means the balance here becomes minus 1, because now we have h minus 1 minus h. But the height still here stays h plus 1, because I still have the larger tree to establish it. If I have two subtrees that are equal in height, and then then that changes and they become unequal in height, but I just did a remove, then I know the reason they became unequal in height is because I removed from one of the subtrees and it shrank a level. With insert, it was different. With insert, we said if you have two subtrees that are equal in height and suddenly they're not, it's because one of them increased in height. On the other hand, I can say if I have two subtrees and I'm doing a remove and they're equal in height before the operation and after the operation, they're not equal in height any longer, then because I was doing a remove, the only possible explanation for that would be that one of them shrank. One of them can't grow if it's removed. That doesn't make any sense. So what I know here is that if I had a balance of 0, it means the two subtrees were equal. When I deleted from one of them in such a way that it shrank in height, that would move the balance from 0 to plus or minus 1. And in those cases, the height wouldn't change because the larger subtree was still there to establish the height. And that was the same situation, again, that we had on the top of the previous slide, where here, just as in the top of the slides for insert, the top of the slides in all these cases were the ones where we went from 0 to plus or minus 1. But in this case, unlike insert, the height stays the same in such a case. We've shrank one of the subtrees, and so they're now no longer equal. The balance is no longer 0. It's now plus or minus 1. But the other subtree, whether this one or this one or this one, is still there to keep the height established. And so that parent's height does not change. Where on the other hand, if I have this situation here where I would say, let's say these were not equal to start with. If I had here, these were both h minus 1, but I had an extra node, so one node keeping this at height h. This whole thing is of height h. This whole thing is of height h. That subtree is only h minus 1. So what I have here is -1 for a balance, h plus 1 for the height. And then I say, let's assume I did a removal of some kind, killed this node, and therefore are left with just this subtree, which is h minus 1. Well, now you see the two subtrees are equal. And so the balance is 0. And you also see because both subtrees are h minus 1, this height must have dropped to h. That is, we said with insertions, when the balance changed from plus or minus 1 to 0, it was because a smaller subtree increased to be equal to the larger one. With removes, it's the opposite situation. If your balance goes from plus or minus 1 to 0, it must be the case that a larger subtree, the larger of the two, if it was plus or minus 1, you had a larger and a smaller subtree, the larger of the two shrank to become equal to the smaller one. You couldn't have the smaller one grow, it's a remove. You don't grow subtrees when you're removing something. That doesn't make sense. So, in a remove situation, you have a situation, if the balance started out being plus or minus 1, you had a situation where you had subtrees of different sizes, and the larger one shrank to become equal to the smaller one, and now because the two are equal, your balance has gone to 0. And in that case, as you can see here, in the case where the balance is gone from plus or minus 1 to 0 for a remove, that means the height of that node must have shrank. Because when the larger of the two subtrees shrinks, that larger subtree was the only one keeping the height established. And so now that that has shrunk to this other level, now the maximum of these two has dropped 1, and so that height has dropped 1 as well. And that was the same thing that went on the bottom of that previous slide. We said these were similar examples where the balance was plus or minus 1. Now I'm shrinking the larger subtree to be equal to the smaller one. The smaller one in both these cases is a null. Null right pointer or null left pointer. And now I'm shrinking the larger of the two subtrees to be equal to the smaller one. Now by killing this node, the left subtree is null, which is the same as the right subtree. Or by killing this node, the right subtree becomes null, which is equal to the left subtree. So I shrink the larger subtree to be equal to the smaller one in height, and that means that that parent node changes in height as well. And down here, same deal. I shrink the larger one to be equal to the smaller one. That means that there's nothing keeping that larger height established, and the parent has to drop a level in height as well. So unlike as with inserts, with removes, when you go from plus or minus 1 to 0, you are dropping a level in height. Your height changes. You'll need to check the parent. because if this subtree has changed in height, its parent, whatever it might be, potentially has a new balance, which may be illegal. And same thing with these up here. In all those cases, the root node of the subtree has dropped a level in height, so we should go up and check its parent's balance. Because if the parent's balance has changed from being whatever it was before, if the parent's balance has changed, it may potentially have been changed to something illegal. And so that's the deal there. That's what's going on. Meaning, if we can come back now and describe what's going on with removes, we'll come back to the rotation example in just a second. So we've got here, with remove, we can say remove actual node, where we have either a leaf, one child, or in order successor. I want to make that clear. When you do a removal of a leaf, like we did here, it's very clear what the parent of the leaf was. The parent of the leaf is, well, the parent of the leaf. It's the node that pointed to that leaf. Likewise, if any of these had been a one-child node and you got rid of it, well, then you would just point this parent to that one child. We had talked about that with binary search trees. So again, if that's the case, when you remove a node, the node that is affected is the parent of that node. So in the case of a one-child remove or a zero-child remove, the node whose balance is affected is the parent of the node you actually got rid of. And when I wrote in order successor here, what I'm saying is when you do a two-child remove, what you are concerned about is the actual physical node you've gotten rid of. Remember, for a two-child remove for binary search trees, what you say is, I'm not really going to remove that value. When I say remove 7 and 7's got 2 children, I don't really remove 7, the node. I just get rid of the number 7, and we said write the in-order successor value into that node's place, and then physically delete the in-order successor. We talked about that with binary search tree remove. So what I'm pointing out here is, because of that, because we haven't physically removed the node that had 2 children, you don't start counting there. What you talk about, what you have physically removed is the in-order successor, and we said when you physically remove an in-order successor, that's guaranteed to be a 1 or 0 child case. And so again, I will have done something like this, where it was either a leaf or I removed a node that had 1 child. The parent of that is where we start counting upwards. The parent of that is where the first balance change occurs. And that's important to keep in mind. So when you do a remove and you say, I've removed a node, start looking at its parent because its parent now has changed, definitely changed in balance. We saw that with insert. When you inserted a node, you were saying convert a null pointer to a one-node tree because you inserted as a leaf, which means then the parent of that null pointer, which is not the parent of that one-node leaf, its balance has certainly changed. We said that. And likewise with all these examples, when you delete a node, whether it has 0 or 1 child, the balance here, the balance of the parent of what you got rid of, has definitely changed. The height maybe didn't change, but whenever you get rid of a node, the balance of its parent has surely changed. And what we're saying is when you do a two-child remove, what we're talking about in terms of check the parent and see if its balance changed is the parent of the actual physical node you deleted, which in the case of a two-child remove will be the in-order successor. You're not actually deleting the node that held your value, you're deleting the in-order successor instead. And so the parent of the in-order successor is where the balance change has occurred. Wherefore, when you get rid of a leaf or a one-child removal case, then it's clearer that, okay, it's the parent of what you got rid of. The in-order successor will fall into those two categories, but we're saying in a zero-child remove case, the parent of the leaf changes balance. In a one-child remove case, the parent of the node you're getting rid of will point to that one child, so that parent of the node you're getting rid of has a balance change. And in a two-child remove case, the in-order successor is what you get rid of, and the parent of the in-order successor is whose balance is affected. And so what we say then is check balance of parent of the now removed node. Or more specifically, the node you removed, when that node was in the tree, it had a parent. Now you've removed that node from the tree, but that node that used to be its parent, that parent is what you want to check. Of course, that parent no longer has the node as a child because you've gotten rid of that node. But that node, the one that was the parent of your removed node, when the removed node was still in the tree, that's what you check. And we did that in all these cases. I removed this node, I checked its parent. 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 And in all 4 cases, the parent's balance has changed. And once you've done that, you then say, if the balance goes from, and then we say, if it goes from 0 to plus or minus 1, the height doesn't change, and so you can stop. And that was the opposite of insert. In insert, that was the continue case. With remove, it's the stop case. And as you do remove examples, you see that occur. That means you had 2 equal subtrees. You shrank one of them. The other one is now larger. I'm sorry. You shrank 2 equal subtrees. That means that you had 2 equal subtrees. You shrank one of them. And the other one is still maintaining the old height. Where when you go from plus or minus 1 to 0, that means the height drops a level, and you would continue by checking the parent. And that was the idea of saying you have a small and a large subtree. The large one has shrunk to be equal to the small one. That's why the balance is 0 now. And so as a result, there's nothing to maintain that large height anymore. Your height of your parent node was relying on this large subtree being large. Now that the only remaining large subtree has shrunk down to being a smaller subtree, your parent's height must have shrunk as well. And we saw that in the examples we've looked at now. And so the other thing to consider is what happens when we do a rotation. And that would be a situation where I had this occur, where I have here h minus 1 with a node, and therefore the entire subtree is h. And this subtree is h plus 1. So since I have h plus 1 here and h here, that means I have a plus 1 balance, and this is h plus 2. And what happens now is I get rid of a node, not from the larger subtree as in the previous examples, but from the smaller one. This is a situation where I have a large and a small subtree, and I delete from the smaller one, making it smaller still. Then the large one is very much skewed against the smaller one in terms of height, and so our balance becomes plus or minus 2. We said if it was plus or minus 1, and you shrank the larger one to be equal to the smaller one, then the balance is 0. On the other hand, if the balance is plus or minus 1, and you shrink the smaller one so that it's even smaller compared to the other one than it used to be, and now if I delete that node, then I'm down to just the h minus 1 subtree. Now there's even a greater difference in height than there used to be. It used to be only 1 level difference between the 2 subtrees. Now we've shrunken the small subtree even further. Now there's a difference of 2 levels. And so in that case, we would do a rotation to fix this. Since I've been messing with the smaller subtree, the larger one still keeps the height intact, so that height stays the same for the moment. Then when I do a rotation, remember the rotation rule. When all is said and done here, the balance goes from plus or minus 2 to 0, and the height drops a level. And in reality, what would be the case here would be that each of these would have become, h in height. But what we're more concerned about is this, because our rule was when you have an unbalanced node, as we do up here, what we're saying then is you have a node that has a balance of plus or minus 2. We're saying then if you run a rotation on that node, when you're done, the balance will be 0, and indeed it is, and the height will have dropped 1 level, and indeed it did. That's our rule, except for the exception, which we're going to see in just a moment. The rule is when you apply, whether to insert or remove, never mind which one, but you've now done the binary search tree operation, you have a node that's got an illegal balance. When you apply the rotation to it, the correct one, the balance becomes 0, and the height drops a level from what it was before the rotation. And since your removal operation didn't increase the height beforehand, as the insert did, As a result, you finish up with a smaller height than you had originally. When you have an original height of h plus 2 here, when I do a removal that makes the smaller one even smaller than it was before, and I throw my parent node into an unbalanced, illegal balance situation, then my rotation fixes things by dropping that balance to 0, dropping that height 1 level, and so the end result is I shrank this subtree so much that I needed to move nodes from this side over to this side to fix things. And in moving nodes from this side over to here, that will shrink this to h, and that will now lower my overall height. Or in other words, rotations, when you have to do a rotation on a remove operation, that will end up dropping the original height. And so when we have a rotation here, when we go from plus or minus 1 to plus or minus 2, we'll do a rotation that brings that balance to 0, but as a result, the height drops a level. We will continue. Which was different than the insert. We said with insert, if you did a rotation, you could then stop after that. You knew you were done. With a removal, once again, these two cases match. They matched with insert and they match now with remove, where we say when you go from plus or minus 1 to 0, it doesn't matter whether you went directly to 0, because as in the case of remove, it doesn't matter whether you shrank the large subtree to be equal to the small one, or whether you shrank the small one even smaller and then did a rotation to make them equal. The point is, in both situations, you started out plus or minus 1 at that node. Ultimately, you ended up at 0. In the insert case, if you started at plus or minus 1 for a node, did your insertion and maybe, if necessary, a rotation, and you ended up at 0 either way, both of those were stop cases. With remove, if you start out at plus or minus 1 before your removal, and you end at 0, whether you did a rotation to get there or not, both of those then, in that case, the overall height of your subtree would have dropped, and you'll have to go up and check the balance of the parent, which makes it a continue case. So as a result, we can say that it is possible when you do a removal of a node, you'll check its parent's balance, and if that parent's balance went from plus or minus 1 to 0, it would have then dropped a level in height. And you'd go up and check its parent's balance, and you went from plus or minus 1 to 0, and therefore you dropped a level in height. So you go up and check its parent's balance, and that balance became illegal. The rotation made it 0, and you dropped a level in height. And you went up to its parent and had to do a rotation there, which means you continue. And you went up to its parent and had to do a rotation there, and therefore you continued. You could potentially, in fact, have done a rotation at every node all the way up to the root. You could potentially have said, I've just deleted this node, check its parent. Oh, its parent needs a rotation. The rotation, when we're done, requires that we go up and check its parent. Oh, that needs a rotation too. And so on and so forth all the way up. With an insert, that can't happen, and we explained why. Once you do that first rotation on a node, whether single or double, you know at that point the parent balance did not change from what it originally was, and so you're done. Where with remove, when you do a rotation, the parent's balance has definitely changed from what it originally was, so you have to go and make sure it's not illegal, and if it is, you do a rotation there as well, and a rotation on its parent, and a rotation on its parent, possibly. So it's possible that a remove would require a rotation on every node upwards, from the parent of what you got rid of all the way up to the root. Where an insert, once you do the first rotation, wherever it happens to be in your tree, then you could stop after that. And so that's sort of the quick summary of things. I'm going to lay the insert slide over the remove. Actually, I'm going to do another of these folds. These top instructions are the insert instructions. These bottom ones are the remove instructions, and you see they're exactly the opposite. In an insert, plus or minus 1, 0 means stop. In a remove, it means continue. That's the middle one here. In a insert, 0 to plus or minus 1 means continue. In a remove, 0 to plus or minus 1 means stop. And then in a insert, needing a rotation means you can stop. And in remove, meaning a rotation means you continue. And you notice that for an insert, the plus or minus 1 to 0 cases are identical. And for remove, they also are identical. Now that's a lot of detail to keep track of, and you may have not gotten it all, understood it all with just viewing the lecture the one time. What I'm saying is jot these patterns down this being the insert patterns, down here being the remove patterns. And as you jot those patterns down, as you do some of the AVL tree examples available on the web page, on the resources part of the web page, as you go through some of those problems, you can take note that these patterns are what you'll see. And so what I've tried to do today is explain these patterns and explain why you're going to see them the way they are. Now in the code, of course, you might not stop right away. You do have to return from recursive calls. The point of this was to kind of more give you an idea of what you're going to expect to see and why with the insertions and the removals. And hopefully it gives you a larger picture of the way the restructuring of the AVL tree starts to work. One last thing to mention, and that is the special case we've referred to. Because we've said usually when you have an unbalanced node and you do a rotation on that node, what that results in is a situation where you go from the unbalanced plus minus 2 to 0 and the height drops a level. We can, however, have a situation that is slightly different than that. And let me say here we have 18. Let me start over so I can put that more in the middle. I have here 18. And we can have here 10 and 15 and 13 and 8 and 9, 13, 15, 18, and then we have here 21 and 23. So we have here h equals 0, h equals 1, h equals 2, h equals 0, h equals 1. This is height 0, this is height 1, this is height 3. Hopefully those heights are clear. The 3 leaves all have height 0. The parent of those leaves has height 1. Then the maximum of those 2 is 1, so that's 2. The maximum of those is 2, and that plus 1 makes that 3. And likewise, the balance of all the leaves is 0. The balance here is plus 1. The balance here is minus 1. The balance here is plus 1. Those are equal heights, so that balance is 0. And that's 1 less than here, so the balance is minus 1 at the root. If you're not sure where those numbers come from, that's definitely something to ask Charles or I about over email, or Adam, I guess. The idea here is you want to be able to understand, you're going to be very confused about everything if you're not still clear on the height and balance ideas. The height of a leaf is 0, the balance of a leaf is 0. The height of a parent node is always the maximum of a subtree heights plus 1. The balance of a parent node is the right subtree height minus the left subtree height. And you can see that here, for example, 1 minus 2 gives you negative 1, and that's why the balance of that 18 is negative 1. 1 and 2, the maximum of those is 2, plus 1 is 3, so that's why that parent node is height 3. So if you have any questions about that, then you want to make sure you ask us. Otherwise, I'm assuming at this point you'll understand where we get our balance and height values, if nothing else. Because I know this is very complicated outside of those 2 definitions. And so what we're going to do here now is say, given this tree, let's say we deleted 23. That would change this height to 0 and this balance to 0. And you'll notice here we say, well, that's 0, that's 2. The balance here becomes negative 2. The height stays the same because you've got the maximum 2 and 0. The maximum of those is 2, plus 1 is 3. So at 18, we have an unbalanced node. But the problem here is, and this can only happen with removes, we ask our first question of those 2 questions we talked about last time. Question 1 was, which of the 2 subtrees is larger? And in fact, it's in height, and it's the left one, because we have a negative balance. And then we say, which of its 2 subtrees is larger? And we have a tie. And as a result, we're going to get a little bit different result. This cannot happen with inserts. With inserts, by definition, the only way we could have gotten an unbalanced node here would be if we had a smaller subtree and a larger subtree, and then the larger subtree increased one more level in height. And the only way that larger subtree could have increased one level in height would be if you had equal subtrees here, and then one of them increased a level in height. And that was what happened all the way back in our examples when we first looked at the single rotation. We first inserted, or we were inserting into subtree A for the single rotation example, and then we were inserting into subtree B for the double rotation example. But in both cases, A and B were the same height. And so when we inserted into one of those two subtrees, the parent of A and B thereby increased in height as well. And we were just looking at that today too. When two subtrees are equal, increasing the height of one of them increases the height of those subtrees' parent, which was K1 in our example. And if you go back in your notes, you'll see that you had K1 with subtrees A and B, and when either A or B increased in height, K1 increased in height as well. When you have two equal subtrees and one of them increases in height, the parent of those subtrees increases in height as well. We just talked about that today as well. And so, as a result, you can't have a tie with inserting. By definition, if I had a problem here, it would be because, in the case of that previous example, K1 increased in height to be even greater than the height of subtree C. And that was what caused the problem in both of those, the single and the double rotation example we looked at. K2 was an unbalanced node back in those examples, if you go back in your notes and look at them. K2 was an unbalanced node because we started out with K1, the left subtree where K1 was the root, being height 1 greater than the subtree C. And then since K1 increased one level in height, now it was 2 greater than subtree C, and so the K2 was unbalanced. Where if we had done an insert that resulted in K1's subtrees being tied, K1 would not have increased in height, and there couldn't have been a problem at K2. And likewise in this example, if by definition if we were doing an insert, if 18 became unbalanced, it would have been because we inserted into one of these two tied subtrees and thereby increased, if we inserted in such a way that one of these two subtrees increased in height, then node 10 would increase in height, and that would have thrown off the balance with this subtree here. So it's not possible to get a tie with inserts, because by definition, if you had an unbalanced node, the breaking of the tie of these two sort of grandchildren subtrees of 18, the breaking of the tie is what made that node increase in height, and therefore would cause the unbalanced situation. If there was no breaking of a tie between these two with an insert, you never would have had the problem to begin with. But with remove, it's possible because we're not messing with this side. These are happily tied, and the reason that there's a bad comparison between these two was not because you inserted into one of these and made it larger, thereby breaking the tie and making 10 greater height. But rather, the reason we have an unbalance between these two is because while these two subtrees were happily tied, the 8 and the 15 subtree, we decreased this one over here, and now these two are not going to be balanced. So that's why this situation can occur with remove. It cannot occur with insert, because in order for the insert to be causing an unbalanced problem, these two would have had to have a tie broken to begin with. Or with remove, these two could be tied because the balance problem is caused by making the other side of the tree too small. And that's exactly what happens here. This side is made too small. 8 and 15, those subtrees are tied. 10 hasn't changed as a result of the removal, but this side has become so small that 10 is, though 10 was minding its own business and was still height 2 just as before, it's now too large compared to the subtree at height. The subtree with root 21, because this subtree has gotten too small. So it's going to need to move some stuff from that side. So when that second question is a tie, when you say the larger of the two subtrees, which of its subtrees is larger, and when you get the answer, neither is larger, they're a tie, that can only happen in a remove case, and in that situation, you'll do a single rotation to move things over. So if we do a single rotation on the right, a single right rotation, we would move 10 up to be the root and 18 down to be the right child, and we'll end up with this tree, where 10 is the root, 18 is the right child. The right subtree of 18 stays the same. The left subtree of 10 stays the same. And the right subtree of 10 moves over to become the left subtree of 18. And this is the situation we have here. You'll notice here the height is 2, the height here is 3, and the balance is +1. That is, for the very first time, and all I'm going to show you is 18 here, the root of this subtree now is not going from 0, ±2 to 0, and the height does not drop a level. Rather, the height stays exactly the same, and the balance goes from ±2 to ±1. That's the one exception to the rule. All the other times, the rotation will result in the unbalanced node, the balance dropping to 0, and the height dropping a level. But in this specific case, where your answer to your second question about which subtrees are larger, whatever, is a tie, then this will be the result. The balance will only drop to ±1, and the height will stay the same. And of course, if the height stays the same, we don't bother with anything. And so when we look at the remove instructions, that would fall into the stop category. So we would, in this case, we went from 0 to, we went in this case from ±1 to ±2, and then back to ±1. And so since we're ending at ±1, this would be the height doesn't change case, and therefore we stop. But that's the one exception to that rule. For every insert, you'll notice that your rotation brings you from ±2 to 0 for balance. And for all removes where those two subtree heights differ, you'll end up with a ±2 brought down to a 0. But in the case where you say which subtree is larger and then which of its subtrees is larger, and when that second question results in a tie, then you'll only end up with a ±1 for your balance. And so your height won't change, and you'll stop, just like in that case. And that's basically it. I know this lecture's done a little late, and I do apologize for that. Keeping on top of stuff is a little difficult on my part, and I will continue to do my best to try not to let things fall so far behind. And I do apologize for that happening. Possibly you've been working AVL examples already. If you have, and you can go back and look at those examples and see that the rules we looked at today are relatively followed and are followed in that pattern. And if you haven't, then as you start going through AVL examples, you can see that the rules we looked at today are followed. Those patterns that we've looked at are the patterns you'll see. And so that might help you kind of gain a greater understanding of exactly what patterns your subtrees are increasing or decreasing as you do various insertions and removals, and so that will hopefully give you a little bit better understanding of what's actually going on. And I'm always of the opinion that if you're not just blindly following an algorithm, if you're actually understanding the way things are shifting and the changes are being made, that will aid you in understanding what you're doing. And so hopefully you'll have a better idea then of exactly how the AVL tree is changing as you do insertions and removals, and therefore how you'll be able to better understand the problems itself, the AVL tree, and it'll make knowing the removal and insertion algorithms more than just pure memorization. You'll actually understand it on a gut level, and after you practice with it some more. And you won't really need to memorize an algorithm so much as you'll just know what has to be done. And that's the level you eventually want to reach, where it's not a matter of memorizing step by step and saying, oh, I forgot a step, I don't remember how it works. You'll just know what to do. And it's at the point where you're not worried about memorizing something for the exam. You'll simply understand things well enough that you can almost sort of redrive the rules on your own. And that's eventually kind of where you want to get to. But anyway, hopefully that helps out and makes things a little bit clearer, or at least gives you an idea of what kind of patterns you'll expect to see. And for the next two lectures, we're going to be looking at B trees, which are a little bit different than you're used to so far. I will be giving that lecture in 5 minutes. You can listen to it whenever you like. See you then.